In this module, we will discuss a major important theorem in mathematics which is called Eurytion's lemma. Though it is a very deep theorem, still it is called lemma. The fact behind this, it has been proved to prove the Eurytion metrization theorem, which says that every regular second countable space is metrizable. To prove this metrizability theorem, Eurytion's lemma was required. That is why this theorem is called lemma. This is probably the first deep theorem in topology. This is called a deep theorem because it involves some new techniques which has never discussed in topology. So, let us go to the slide presentation. As we have told, now we shall gradually move to Eurytion metrization theorem. We mentioned that the key role between the Eurytion metrization theorem is Eurytion's lemma. So, let us start with Eurytion lemma. A topological space X is normal if and only if for any two disjoint closed sets E and F there exists a continuous function f from x to r such that f of E is equal to 0 and f of capital F is equal to 1. In fact, in this theorem there is nothing special with 0 and 1. We can take any two distinct real numbers. Intuitively, this theorem can be said in this way that a topological space X is normal if and only if any two disjoint closed sets can be strongly separated by a continuous functions. In the definition of normal spaces, we have seen that a topological space is normal if and only if they can be strongly separated by disjoint open sets. The beauty of Eurytion's lemma is that a topological space is normal if any two disjoint closed sets can be strongly separated by continuous functions. The Eurytion lemma also gives on a normal space a rich source of continuous functions. In fact, for any two disjoint closed set, this gives a continuous functions. Let us come to the proof of this theorem. Let E and F be two disjoint closed sets and V is equal to x minus F. Then V is an open set containing E. Then by normality lemma we have that there exists an open set, let us denote it by U half, such that E is contained in U half, is contained in U half closure, is contained in V. We can see in this inequality that E is contained in U half, where E is a closed set and U half is an open set, and U half closure is contained in V, where U half closure is a closed set and V is an open set. Therefore, we can push an open set between E and U half and another open set between U half closure and V. So, let us rename them as U1/4 and U3/4. In this way, we have that following inequality. that is E is contained in U 1/4, is contained in U 1/4 closure, is contained in U half, is contained in U half closure, is contained in U 3/4, is contained in U 3/4 closure, is contained in V. Note that these numbers 1/4, 3/4, these numbers are dyadic rational number. In this way, we can get a chain of dyadic rational numbers. So, continuing this manner, for each dyadic rational number r less than 1 greater than 0, we get an open set UR such that UR is contained in US, where 0 less than R less than S less than 1, E is contained in UR, where 0 less than R less than 1, UR is contained in V, where 0 less than R less than 1. With this information, now we shall go to define the continuous function f. We define the function f so that the set del u are level sets of f on which f assumes the value r. This is done by defining f(x) is equal to 0 if x belongs to UR for all r greater than 0, and f(x) is equal to supremum of r such that x does not belongs to UR. Clearly, f is bounded by 0 and 1. F is equal to 0 on E and f is equal to 1 on f. So, it remains to show that f is continuous. Let x belongs to capital X. Let x belongs to capital X. For convenience, we assume that 0 less than f(x) less than 1. The case f(x) is equal to 0 and f(x) is equal to 1 are not difficult. Let epsilon be positive. Let us choose a dyadic rational number 0 less than r less than s less than 1 and f(x) minus epsilon less than r less than f(x) less than f(x) plus epsilon. Then x does not belongs to ut for dyadic rational numbers between r and f(x), so that x does not belongs to UR closure. On the other hand, x belongs to ux. Hence, W is equal to US minus UR bar is an open neighborhood of x. If y belongs to W, then from the definition of f, we see that r less or equal to f(x) less or equal to s. In particular, mod of f(x) minus mod of fy less than epsilon for all y belongs to W, so that f is continuous at x. Hence, we have proved that if x is a normal space and E and f are two disjoint closed sets, then there exists a continuous function such that f of E is equal to 0 and f of f is equal to 1. The converse part is easy. In fact, let the converse part holds. That means, for any two given closed sets E and f, we get such a function. Now since E and F are given closed sets and f of E is equal to 0 and f of capital F is equal to 1, let us take f inverse minus half to half this open interval and take also f inverse half to 3 by 2 this open interval. Then these two open set are disjoint and contains E and F respectively. So this says that X is normal. This completes the proof of Eurytion's lemma. Next we shall prove that a strong form of Eurytion's lemma. In Eurytion's lemma we have proved that if E and F are closed sets, in fact disjoint closed sets, then there exists a continuous function f such that f is 0 on E and f is 1 on capital F. But this does not guarantee that f inverse 0 is equal to capital F. We can say that if E is a closed G delta set in a normal space, then there exists a continuous function such that f inverse 0 is equal to E, which we present in the following theorem. Let X be a normal space, then there exists a continuous function f from x to 0 1 such that fx is equal to 0 for all x belongs to A and fx greater than 1 for all x does not belongs to A if and only if A is a closed G delta set in X. Suppose there exists a continuous function f from x to 0 1 such that fx is equal to 0 for all x belongs to A and fx greater than 0 for all x does not belongs to A. Then A is equal to f inverse 0 must be closed. Then A is equal to intersection f inverse of minus 1 by n to 1 by n, and each f inverse minus 1 by n to 1 by n is an open set. Hence, A is a Z delta set. That means, if such continuous function exists, then A is a closed G delta set. Conversely, let A be a closed G delta set, then there exists a sequence un of open sets such that A is equal to intersection of un. That means A is disjoint from each x minus un, where each x minus un is a closed set. So, by Eurytion's lemma, for each n there exists a continuous function fn such that fn of A is equal to 0 and fn of x minus un is equal to 1. Now, we construct a continuous function small f as sum of modulus of fn by 2 to the power n. Then f is a continuous function. One can check that f vanishes on the set A and f does not vanishes outside A, so that f inverse 0 is equal to A. Therefore, in the Eurytion's lemma, we have seen that X is normal if and only if any two disjoint closed sets can be separated by continuous functions. In the definition of normal space, we have seen that a space is normal if and only if any two disjoint closed sets can be separated by disjoint open sets. Now, if we come to the definition of regular space, then we have seen that a space is regular if and only if any point and closed set can be strongly separated by disjoint open sets. Therefore, it is very much natural to ask whether that in regular space also such continuous function exists. That means in regular space also there exists a continuous function such that which vanishes at a point and becomes 1 on that closed set. The answer is no. So, this leads us to the definition of a new topological spaces. As we have discussed, we are going to define completely regular space. In this connection, we shall mention that there are topological spaces which are called functionally Hausdorff spaces. As we have seen that in case of normal spaces, separability by disjoint open sets and continuous functions are equivalent. But in case of Hausdorff spaces, separability of 2 points by disjoint open sets and separability of 2 distinct points by continuous functions are not same. Though we are not providing any example, but we mention the definition that if topological space X is said to be functionally Hausdorff if for any 2 distinct points there exists a continuous function f which is 0 on one point and 1 in other point. Next, before defining completely regular space, we must say that we require an example of a regular space which is not completely regular and an example of a completely regular space which is not normal. First, we will provide an example of completely regular space which is not normal. This will be provided by our developed machinery, but the example of a regular space which is not completely regular will be extremely difficult and should be provided at the end of this section. So, first we define completely regular space. A topological space X is said to be completely regular if all finite subsets of it are closed and for any x belongs to X and any closed set F not containing X, there exists a continuous function f from x to r such that f of x is equal to 0 and f of capital F is equal to 0. That means a topological space is completely regular if and only if point and closed set can be strongly separated by continuous functions. It is clear that completely regular space are regular. In fact, let a space X be completely regular, let X be a point and F be a closed set not containing X. Then by the definition of complete regularity, there exists a continuous function f such that f(x) is equal to 0 and f of capital F is equal to 1. Now consider disjoint open intervals containing 0 and 1 and take their inverse image under F, then these inverse images are open sets, disjoint and contains X and contain capital F respectively. So, this means that completely regular space are regular and normal space are completely regular. It follows directly from Eudition's lemma. Next, we shall prove that completely regularity is a hereditary property. The proof is not difficult at all. Let X be a completely regular space and Y be a subspace of capital X. Let small x be a point of capital Y and let capital K be a closed set of Y disjoint from X. We choose a closed set in capital X such that K is equal to H intersection Y. Therefore, X does not belongs to H. Since X is completely regular, we can choose a continuous function f from x to r such that f(x) is equal to 1 and f of capital H is equal to 0. Now, taking the restriction of f to y, we get the required continuous function on y. Next, we prove that product of completely regular spaces is completely regular. Let X alpha be a collection of completely regular spaces and let capital X be the product of X alpha. Let us consider a point x is equal to X alpha of capital X and let U be an open set of X containing X. Then U is equal to product of U alpha where each U alpha is open in X alpha and U alpha is equal to X alpha except for finitely many alphas, say alpha 1, alpha 2, alpha k. Then for each alpha I, we can choose a continuous function f I from x to r such that f of alpha I of x alpha I is equal to 1 and f of alpha I of x alpha I minus u alpha I is equal to 0. Now, let us set phi alpha I is equal to f of alpha I composition pi alpha I. Then, being composition of two continuous function, each phi alpha I is continuous from x to r. Now, if we set phi is equal to product of phi alpha 1, phi alpha 2 and phi alpha k, then it is easy to observe that phi x is equal to 1 and phi of x minus u is equal to 0. So, this proves that product of completely regular spaces is completely regular. Before ending this module, we provide our promised example of completely regular space which is not normal. We have proved that S omega Cartesian product S omega plus 1 is normal. Now, both S omega and S omega plus 1 are normal spaces. So, they are completely regular. So, as we have proved in the last theorem, the product of completely regular space is completely regular. We have that S omega Cartesian product S omega is a completely regular spaces, but we have already shown that this is not a normal spaces. So, we get an example of a completely regular space which is not normal. Therefore, in this section or in this module we have discussed about Eurytion's lemma, completely regular space, and an example of a completely regular space which is not normal. With this we end this module. Let us pass to the next module.